Hello, I'm Gusti Shintya Muliarta, 1311823. I'm here to do an experiment to investigate the effects of input voltage on performance of magnetohydrodynamic ship. So, magnetohydrodynamic expresses the motion of electrically conducting fluid, or a plasma, flowing when electric and magnetic fields are present. It is also usually referred to as magnetofluid mechanic or hydromagnetic. The electrically conducting fluid can generally be described by a demeanor of its components, such as electrons, ions, as well as neutral particles. The magnetic properties can also impact by increasing quantities such as magnetic viscosity, pressure, Reynolds number, diffusion, which contribute to the fluid mechanics. Nowadays, its applications are continuously studied and proven to be useful in various fields, such as solar winds, submarines, ships, spacecraft, as well as biomedical sensors and actuators. The propulsion of magnetohydrodynamic ship does not utilize any moving part, which means that it is much quieter. It is also able to develop in ways ranging from inductive to conductive systems, with duct in internal systems or surrounding fluid in external systems. Even so, the efficiency of the magnetohydrodynamic thruster is actually below other common devices due to the limited strength of magnetic fields currently available until this day. It is the aim of this experiment to investigate the deviation in speed of the magnetohydrodynamic ship and the drag force acting on it due to the charge induced by the presence of electric current and a neodymium magnet in different conditions, such as varying input voltage. The analysis will include a range of studies such as fluid mechanics, electrical circuits, and electrolysis. The hypothesis of this experiment is that as the input voltage increases, the speed of the magnetohydrodynamic ship also increases, and so does the drag force acting on it. This experiment's objectives are to analyze the impact of different input voltage upon the speed of the magnetohydrodynamic ship, and to determine the drag force acting on the magnetohydrodynamic ship at different velocity. The investigation of magnetohydrodynamic drive is done by passing a current through an electrically conducting fluid in the presence of magnetic field, and includes the coupling of electromagnetism explicitly with respect to induction to dynamics. It is vital as the relative motion of electrically conducting fluid is influenced by the external magnetic fields. This is why the effect of magnetohydrodynamic drive can be directly affected by the magnitude and direction of fluid flow as well as magnetic field. In this experiment, the neodymium magnet will provide magnetic field while electric current is passed through the two bars of aluminum bars that are connected to the power supply. When the main switch is turned on, the hydroxide ions will travel to the positive electrode while the H+ ions will flow to the negative electrode. This will result in a flow of charge around the magnetohydrodynamic ship. Ions will flow in a direction which is perpendicular to the electric current and generate the flow of water around them. The voltage difference between the two aluminum bars, which act as electrodes submerged in electrically conducting fluid, produces fluid electrolysis. The fluid is an electrolyte, which in this experiment we are using salt water or NaCl solution. At the cathode, the water will undergo reduction process in which the water will be dissolved to hydroxide and hydrogen gas. Whereas at the anode, the chloride will be oxidized to chlorine. Thus, the overall electrolysis of aqueous NaCl solution will develop hydrogen as well as chlorine gas as products. We can calculate the drag force using this formula. The drag force is half times the product of fluid density, total cross-section area of the ship that's in contact with the electrolyte, with the total drag coefficient of the ship, as well as the square of mean fluid velocity. The total drag coefficient is made up of skin friction drag coefficient, form drag coefficient, as well as wave-making drag coefficient. For the skin friction drag coefficient, we can determine it using the formula shown. It utilizes the kinematic viscosity as well as the immersion depth of the thruster top. And for the form drag coefficient, it depends on the shape of the magnetohydrodynamic ship, and for this case, the form drag coefficient is 1. For the wave-making drag coefficient, because this experiment is done on shallow water, the wave-making drag coefficient is 0. In order to use the skin friction drag coefficient, we have to make sure that the Reynolds number is less than 5 times 10 to the power of 5. And to check whether the wave-making drag coefficient is really 0, we have to determine the Froude number, and then we see from the graph shown. So for the experiment, we're gonna need several apparatus, which are neodymium magnet, aluminum bars, alligator clips, power supply, container, wire, salts, water, knife, measuring cup, weight scale, styrofoam, 9-volt battery, scissors, tape, table, as well as ruler. So to construct the magnetohydrodynamic ship, we have to cut the styrofoam board into two pieces with 10 cm length and 9 cm width using a knife. And then stack both pieces of styrofoam together using tape. Tape the neodymium magnet into the center of one of the stacked styrofoam surface. Place the aluminum bars on either side of the neodymium magnet and secure it to the stacked styrofoam by using tape. Put and tape the 9-volt battery on the other surface of the stacked styrofoam and attach the alligator clips to the wire. Connect each aluminum bar to the pole of the battery by using the alligator clips, and then measure the height using ruler, as well as the weight of magnetohydrodynamic ship using the weight scale. This is what the magnetohydrodynamic ship would look like, and before conducting the experiment, please remember the safety assessment, which are: don't touch the electrical equipment with wet hands, always turn the main switch off when they are not used, and make sure all wires are arranged neatly and out of harm's way. First, fill the container with 0.8 liters of water using measuring cup, and then put in the 1.25 kg of salts, and then stir well. Wait until the water inside the container is calm, and then place the magnetohydrodynamic ship into the water. Measure the time needed for the magnetohydrodynamic ship to travel across the container, which is 30 cm, and then calculate the speed of the magnetohydrodynamic ship when the input voltage is 9 volt. This is the pre-experimental procedure in order to measure the accuracy of our experiment later. Moving on to the actual experiment, we have to disconnect the aluminum bars from the 9-volt battery, and then remove the 9-volt battery from the magnetohydrodynamic ship, and then position the power supply on the table, higher ground than the water container, and attach the alligator clips joining the aluminum bars to the power supply. Make sure that the power supply is off, and then place the magnetohydrodynamic ship on the 0.8 liters of water in the container that have been added with 1.25 kg of salt. Ensure that the wires are not submerged in the water and wait until the magnetohydrodynamic ship is settled on the water. Tape the wire into the table so that the wires will be organized neatly without any part of it getting in the way. Turn the knob of the power supply to the desired input voltage and turn the switch on. Measure the time needed for the magnetohydrodynamic ship to travel around 15 cm, and then turn the power supply off. You can hear that there's a hissing sound, which indicates that there are effervescence or bubbles forming as a result of the magnetohydrodynamic drive. Repeat the previous steps with different input voltage. From the experimental results, we can see that the time taken for the magnetohydrodynamic ship to travel 15 cm actually decreases as the input voltage is increased, which means we can get the speed of the ship by dividing the distance, which is 15 cm, by the time taken. And as we can see here, that the speed of the magnetohydrodynamic ship increases as the input voltage also increases. Now, to ensure the accuracy of this finding, we'll look back to the pre-experiment data that we previously procured from the experiment using the 9-volt battery instead of a power supply. Now, we can see that the speed of the magnetohydrodynamic ship with power supply at 9 volt and with the 9-volt battery is actually quite similar. There is only a slight deviation between the results, which means that our findings has sufficient accuracy. Here we can see the correlation between the speed of the ship with the input voltage. Next, to determine the drag force acting on the ship, we will determine the Reynolds number and make sure that it is all less than 5 times 10 to the power of 5 in order to use the previous formula for skin friction drag coefficient. And for the Froude number, we have to make sure that all of the number is less than 0.1 in order to validate that the wave-making drag coefficient will be 0. Next, substitute all the known parameters into the formula and we will obtain the skin friction drag coefficient. And then, add all the skin friction drag coefficient, the form drag coefficient, and wave-making drag coefficient to obtain the total drag coefficient. After obtaining the total drag coefficient, we can now determine the drag force acting on the magnetohydrodynamic ship at different velocity. We can now construct the graph correlating the drag force acting on the ship to the speed of the magnetohydrodynamic ship. After executing the experiment, it is found that the time taken for the magnetohydrodynamic ship to travel across the 15 cm distance keeps on decreasing as the input voltage is increased. This results in higher speed that the magnetohydrodynamic ship possesses when it is provided with higher input voltage by the power supply. This hypothesis is proven and supported by the experimental results attained. It also shows that the magnetic potential is legitimately proportional to the current and magnetic field. The higher the input voltage is, the more current is applied and passed through the electrically conducting fluid when magnetic field is present due to their directly proportional relationship. This means that the larger potential is developed when the input voltage is increased. The correlation between the input voltage and speed of the magnetohydrodynamic speed is agreed upon both in theory as well as in practice. However, we have to make sure that the results of this experiment is accurate by comparing it to another experiment using a 9-volt battery instead of a power supply. When using a power supply, there will be errors that are caused by the access wire which connect the magnetohydrodynamic ship to the power supply itself. The wire can be submerged underwater and provides a pull to the magnetohydrodynamic ship, which in turn reduces the speed of the ship. This is why the access wire has to be taped to the table in order to keep it tidy and away from the salt water. We then compare the results of the magnetohydrodynamic ship using both sources of voltage at 9 volt, while maintaining other control variables such as distance between the aluminum bars and concentration of salt in water. The percentage error between the two experimental results is only around 8%. Lastly, the drag force acting on the magnetohydrodynamic ship is calculated by previously acquiring the total drag coefficient made up of skin friction, form, as well as wave-making drag coefficient. In order to utilize the skin friction drag coefficient formula, we have to make sure that the Reynolds number is less than 5 times 10 to the power of 5, and it is discovered that for all speed of the ship, the Reynolds number satisfied the criteria, which means that all the flow can be considered to be laminar flow. From all the data gathered from the experiment and obtained from the calculation, we can then find the drag force acting on the magnetohydrodynamic ship at different velocity. It is shown that as the speed of magnetohydrodynamic ship increases, due to higher input voltage applied, the drag force acting on the ship also becomes greater. In theory, we can actually see from the formula of drag force alone that the square of the mean fluid's velocity is directly proportional to the magnitude of drag force acting on the magnetohydrodynamic ship. This means that the phenomenon in which the drag force increases with higher speed of magnetohydrodynamic ship is agreed upon in theory as well as in practice. In conclusion, it is discovered in this experiment that the input voltage ranging from value of 6 volt to 15 volt will generate the speed of magnetohydrodynamic ship ranging from 0.01 meter per second to 0.03 meter per second. With increasing input voltage and higher speed of magnetohydrodynamic ship, the drag force acting on the ship also becomes greater. The drag force itself varies from least magnitude of 0.004 Newton to the largest magnitude of 0.02 Newton. For this experiment, I would suggest using LiPo battery or lithium power battery instead of power supply to vary the input voltage. This is because when using the power supply, there will be excess wire hanging and even submerged in the salt water. This creates a pull and makes it harder for the ship to move forward. The joint wire will clearly reduce the actual speed of the magnetohydrodynamic ship as it will slightly hold back the ship and there will be energy wasted by the ship to overcome the pulling force generated by the wire. Furthermore, it will also be easier to record the time taken, and the magnetohydrodynamic ship will cover larger distance when using the LiPo battery. This is because the magnetohydrodynamic ship will not be attached to anything and doesn't have to be mindful of the available length of the wire. Even though the magnetohydrodynamic ship will surely be heavier with a battery tape on top of it, the ship will be free to cover any accessible distance. Thus, this will create a more accurate representation as it resembles a more realistic ship in practice. Thank you so much for listening.